Hi everyone, this video covers 1.2 Functions and Their Properties Part 1. Alright, a few definitions: function, domain, and range. A function from set D to set R is a rule that assigns to every element in D a unique element in R. The set D of all input values is the domain of the function, and the set R of all output values is the range of the function. Alright. Vertical line test. You guys have probably seen this before. Basically, if you are trying to determine if a graph is a function, you can draw vertical lines, and if any vertical line intersects the graph more than once, then it's not a function. The technical definition of the vertical line test states that a graph or a set of points xy in the xy plane defines y as a function of x if and only if no vertical line intersects the graph in more than one point. So, I think I'm going to let you guys try, I'll do this one. Which of the following graphs is not a function? Well, if you draw vertical lines on these graphs, wherever I draw a vertical line, it's only going to hit the graph one time, no matter where I draw it. But here, it hits the graph multiple times. So this is not a function. Alright, find the domain of each of these functions. Okay, when you're dealing with a square root, let me write this over here. In order to attain a real solution, square roots must be greater than or equal to 0. And in fractions, denominators cannot be equal to 0. So, if I'm looking for the domain of this, what's inside my square root, in this case x plus 3, this must be greater than or equal to 0. So if I solve for x must be greater than or equal to -3. In interval notation, that is -3 to infinity, including -3. Now down here I have both a square root and a denominator, so x has to be greater than or equal to 0, and x minus 5 cannot equal 0, so x cannot equal 5. So here my interval is going to be 0 to 5, not including 5, and 5 to infinity. Okay, let's go on to the next page. Okay, so here I have s squared. There's no variable in the square root, and there's no variable in the denominator. So technically, it's all real numbers. I can plug in anything for s. But then it asks, what is the implied domain of C? Of part C. Originally I had letters next to these. Sorry about that. Okay, so sorry, I paused the video for a second because there's a few typos in this question. It says what is the implied domain. It should say what is the relevant domain. What is the relevant domain of part C, the previous problem, where A of S is the area of an equilateral triangle, no S, with side length S. Now, if you think about it, you can't have a side length, a negative length. It has to be positive, and so it can't be negative and it can't be 0. S has to be greater than 0. So my relevant domain is going to be 0 to infinity. The number can be as big as we want. It just has to be positive. Alright, example number 3. Find the range of the function f of x equals 2 over x. The best way to find range is to graph it. So let's pull out our graphing calculators. Y equals 2 over x. Graph, whoops, you know what? I still have my scatter plot on from the previous class. And let me change my window. There we go. Okay, so domain is the x values, range is the y values. As you can see, if you look vertically, the graph exists from negative infinity all the way to 0, and then there's this break. There's this discontinuity in the graph at 0. And then it continues from 0 all the way to infinity. So the range is going to be negative infinity to 0 and 0 to infinity. Okay, example number 4. One of the most important properties of the majority of functions that model real-world behavior is that they are continuous. However, that is not the case for all functions. Look at each of the graphs below, it's actually on the next page, and match them to the appropriate description. So if you look on the subsequent pages, there are some graphs, and the challenge is to figure out which of these graphs match which of these definitions. I'm actually going to let you guys try this one. We will go over the answers in class, but I bet that you guys will be able to figure out most of these just from the descriptions given. But we will go over the answers in class. All right, example number 5. Which of the following graphs is discontinuous at x equals 2? So we're looking at x equals 2. Here is x equals 2, x equals 2, x equals 2. So we're looking on this dotted line. So which of these graphs is discontinuous? This doesn't appear to be discontinuous, but this one does. And this one, if you look very closely, there's this tiny break in the graph there. So these two graphs appear to be discontinuous. All right, let's go on to the next page. All right, for each function, tell the intervals on which it is increasing and the intervals on which it is decreasing. Okay, so let's graph this. So I've got x plus 2 squared. So there's my graph. Okay, it appears to be, let's see if I can keep this on here. It appears to be decreasing from negative infinity to 2. And increasing from negative 2, from negative 2 to infinity. Notice that it is both increasing and decreasing at negative 2. Alright, and I'm going to let you guys try the next one. We'll go over the answer in class. And that's all the notes for this section. Thank you so much for watching.